First of all, I'd like to thank the local organizers and the program committee for making this great conference to happen under this bad situation of Corona pandemic. So let me begin. So I'll be talking about a generalization of the Chvátal-Gomory closure for integer programming. And this is joint work with Sanjeev Dash from IBM Research and Oktay Gunluk from Cornell. I'm guessing everyone knows what it is, but let me briefly explain integer programming. I'll be focusing on the linear case, by the way. So that is, I'm given a linear function W transpose X, and my goal is to find an integer point satisfying a linear system of inequalities, maximizing this linear function. In picture, the linear inequalities correspond to a polyhedron, and I want to find a lattice point or an integer point inside this polyhedron that's maximizing this linear function. In practice, what we do is to relax this integrality condition and optimize a linear function over this polyhedron. If we get an integer solution, then we are great. But if not, we should do something else. And what should we do? The most naive thing we can try is to round every fractional coordinate. Then we get the nearest integer point to this LP optimal solution. But the problem here is that we don't even guarantee the feasibility of this nearest integer solution. In fact, the actual IP optimal solution might be quite hidden inside this polyhedron. So we need to do something different. What we do is what we call cutting plane method in combination with enumeration, that is branch and bound. A cutting plane or a cut is a linear inequality that potentially cuts off some part of this polyhedron while keeping the same set of integer points. Okay. So by adding a cutting plane, we can reduce the search space in the hope of getting closer to this optimal integer point. Okay. So we basically recursively add cuts until we obtain an integer feasible solution. So Chvátal and Gomory introduce a very nice and simple way of generating cuts. So that is, given an integer coefficient vector, let us consider this inequality. If you take a look at the right-hand side, this is the maximum value of this linear function over the points in P. So by definition, this inequality must be valid for every point in P. Okay. But we look at integer points inside P. So if you take an integer x, the corresponding C transpose X value should be an integer. But it's possible that the right-hand side is still fractional just because the LP optimal solution has fractional coordinate. In that case, we can round down the right-hand side and we still keep the validity of the inequality for the solutions for the integer solutions in P. So this is basically Chvátal-Gomory cut. And throughout this talk, I'm going to call it a CG cut in short. The CG cuts are quite prominent in combinatorial optimization and linear and nonlinear integer programming. So some important classes of inequalities for combo problems are known to be CG cuts. And there are some works on implementing CG cuts for solving general integer linear programs. People have also looked at CG cuts for nonlinear integer programs. And recently, these people proved that some important classes of binary polynomial optimization, important classes of cutting planes for this problem are known to be CG cuts. Okay. Let me move to a notion of closure after defining CG cuts. So that's basically given a polyhedron, and I apply all possible CG cuts for this polyhedron P. And because every integer vector corresponds to a cut, we have an infinite number of CG cuts. But Scriber proved that if you start with a rational polyhedron, then only a finite list of CG cuts can be non-redundant. So infinitely many of them are, redundant. So this is a nice result. So in picture, if you start with a rational polyhedron, I like to get closer to these black integer points in a hope that I find an integer solution that's maximizing my objective function. So if you apply the CG closure, you obtain this. So this is smaller than the original polyhedron P, but also this is defined by a finite number of linear inequalities. So again, if you take a rational polyhedron and its CG closure, then it's a polyhedron. By polyhedron, I mean that it's defined by a finite list of inequalities. Okay. And it was a long-standing open question whether the same thing holds for irrational polyhedron. That's basically a bounded polyhedron whose data contains some irrational number. Okay. Actually, it turns out to be a polyhedron as well, and it's kind of proved by Dunkel and Schultz. And around the same time, the same thing holds for any closed convex set that's bounded. Okay. So CG closure of a closed convex set can be defined similarly. Basically, instead of the max function in the right-hand side, we have the support function right here. Okay. So the goal of today is to study a generalization of the CG closure and understand when it's a polyhedron. Okay. So to explain how we generalize CG closure and CG cuts, let me get back to the definition of CG cuts and explain the geometric interpretation behind it. Linear inequality here, and we round down the right-hand side to get a CG cut. Okay. So the procedure of this rounding down the right-hand side kind of corresponds to moving this hyperplane a little bit upward until it hits an integer point here. So this integer point will block you from moving this black hyperplane upward. You just stop right here. And this red hyperplane cuts off this small region of this polyhedron. Okay. But sometimes maybe this blocking integer point is far and irrelevant from your polyhedron P. Okay. What if you kind of know that the set of feasible integer solutions are contained in a smaller set S? Okay. Maybe for convolved problems, you know that the integer variables take only the binary values. Okay. So in this case, you should look at blocking points inside this S. Okay. And then you can try to move your hyperplane a little bit further. So you stop right here. And then potentially you can remove more region of this polyhedron P. So algebraically, we have this maximum value and right-hand side, and then we took the floor of that. And this floor can be rewritten as the following. So you are looking at an integer point that's closest to this black hyperplane, the initial hyperplane. So that's the blocking point from the lattice space. Okay. The value for the new inequality would be just obtain replacing this Cn by S. So you are finding an integer point in S that's closest to this black hyperplane. That will be the blocking point. Okay. So the difference is that the gap between the original value and the floor is always less than 1. But that's not the case in this generalization. So what it is so this gap can increase as a function of this coefficient C. So if you take a large coefficient vector, then this gap will be arbitrarily large. Okay. So this is basically how we generalize CG cuts, given the information about the integer feasible solutions. And then we'll call it S Chvátal-Gomory cut or S CG cut in short. Okay. So remember that the CG closure is obtained by adding all possible CG cuts. We can do the same thing here. We just apply all possible S CG cuts, and then we obtain a closure P subscript S. And this idea was introduced by Dunkel and Schultz and Fukuta like about 10 years ago. And I'd like to mention this. So SCG cuts are somehow intersection cuts from what are called S-free splits. And this S-free splits were introduced by these people. So Bonami, Tramontani, Lodi, and Wheat. This is IPCO 2017 paper. I'm not going to mention what intersection cuts are. Well, this is beyond our scope. But let me mention that intersection cuts have been studied a lot in the last decade in the integer programming community. I'm just mentioning this just to highlight that this derivation of this SCG cuts were inspired by a lot of these activities on, geometric approaches to integer programming. I guess, do we have any questions before I move on to the technical part? Okay. For the rest of my talk, I'll try to motivate the result and explain the details. Okay. So Bonami and Wiz 3 years ago raised a question about whether the S-split closure is a polyhedron. Okay. Our setting is slightly different. So our CG closure is defined by a subclass of S-split cuts. Okay. Regarding this setting, Dunkel and Schultz proved that SCG closure is a polyhedron if the S is the set of binary points. Okay. So motivated by this result and this question, we recently proved the following result. So if S is the set of integer points satisfying some bound constraints, then we have the same statement. So one part of variables have lower and upper bounds, but another set contains just one-sided bounds, but maybe you could also have unrestricted variables. And this result generalizes the binary case and the traditional setting, and also non-negative integer case. And our result is that you can take any integer points inside a polyhedron defined by a linear inequalities, you still get a polyhedron. So this is the main statement of our paper. Okay. So in the remaining 10 minutes, I'm gonna explain how we prove this. Okay. So the challenge is that if you take a CG cut, this gap was less than 1. If you take an integer vector with large coefficients, then this quantity goes to 0. And note that this quantity just measures the distance between the two hyperplanes. Okay, this distance goes to 0, which means that the part of polyhedron cut off by this hyperplane, the inequality, is getting negligible. So in the end, CG cuts with large coefficients will be redundant. Okay? We can only focus on cuts with bounded components that will kind of restrict your choices. But that's not the case for the SCG cut. So in fact, there could be a lot of non-redundant SCG cut that have large coefficients. So this is one challenge that kind of makes us hard to use previous result for proving our result. Okay, so the finite case is separately dealt with. So the idea is if you take a linear inequality, and then if you look at a finite set of integer points, then this inequality will partition the set S. So one set contains the points above this hyperplane, and the other set contains the points below this. Okay? But you can kind of reverse engineer this process. Basically, you are given a partition, specific partition, and I like to kind of enumerate all possible SCG cuts that will give me this partition. Okay, so I'm given this partition L and G, and I'd like to understand when this SCG cut alpha transpose X less than or equal to beta give me this partition. This can be done by writing down these conditions on alpha and beta. So alpha and beta take integer values, and then as long as alpha and beta satisfies this set of linear inequalities, then this will give me this partition, and also this is corresponding to SCG cut. And because S is finite, we know that L and G are finite sets. So this corresponds to a polyhedron. So you are enumerating integer points inside a polyhedron. Okay. But the problem is this can be unbounded. But the important inequalities correspond to extreme points and extreme rays of this polyhedron. We can kind of only focus on finite number of pairs.
Dabeen, you have 5 minutes now.
Okay. So the difficult case is obviously when you have infinitely many integer points. So the difficult case is when S is a cone, infinite cone. Okay. But we kind of want to get back to the finite setting somehow. So what we do is we take a relaxation of this integer set. Okay. So instead of taking just non-negative combinations, we take any linear combinations. And because this set contains S, the original set, the corresponding closure is a relaxation of the SCG closure that we want to look at. Okay. So if this S0 CG closure is a polyhedron, then you can ignore SCG cuts that are S0 CG cuts that do not, cut off any point from this. How do we show that? We use somehow a unimodular mapping lemma, basically to prove that this this set is a polyhedron. We can focus on the thing obtained after taking this unimodular mapping. Okay, and the thing is, because this S0 is a set of integer points in a linear subspace, you can show that there's a unimodular mapping that maps this to the set of this form. And this is one setting we have already settled in the previous paper. So it proves that the PS0 is a polyhedron. Okay. Now we have to kind of look at SCG cuts that are not S0 CG cuts and also non-redundant. The first property we can prove is that if you take a look at the corresponding hyperplane and the direction perpendicular to this hyperplane, this direction should be aligned with the ray directions. If you look at this hyperplane, the direction is not aligned with the rays. You know that the intersection kind of goes to infinite space, so that there could be a lot of integer points around this hyperplane that are blocking this hyperplane from being moved. Whereas if you look at this black hyperplane, then there are not many integer points blocking you from moving it. So basically, you have to look, you can just focus on these inequalities. So basically, you can just focus on inequalities that are leaning on the walls of rays. And then in the end, you can show that the intersection point of this hyperplane and the rays can be bounded in a small box. That's how we kind of get back to the finite case. Okay. This is the most important lemma in our paper, by the way. Just to highlight, just to outline how we prove this, you can argue that alpha and beta can be obtained from a non-negative multiplier, and this guarantees that the intersection points are small. So you want to show that the ratio is smaller. Okay. What we can show is that if the components of this multiplier are balanced somehow, then we can find such a small m. So if not, what we do is we find another multiplier that are kind of approximating large components of this the initial multiplier lambda, and then set the other components to 0. Okay. And then you just take out this delta from lambda so that you make it more balanced. And more importantly, we want to show that the corresponding SCG cut dominates the original one. Okay. We can prove that such a vector delta exists. Okay. So this is the end of the story for the cone case. In general, we have possibly many vertices in our convex hull. Also, convex hull might not be pointed, but we can take care of that separately, actually. And then in summary, we proved this result. So if you take a look at integer points inside any polyhedron and then use it to obtain the CG closure, then this is always a polyhedron. Okay, this is it. Thank you.
Thank you so much, Dabeen. I will wait with the applause until we are done with your part of the session. I just see that there was one question during your talk from Matthias Walter. Maybe he can ask that question himself. Matthias, please go ahead.
I can do so. Thanks. Yeah, thanks for the nice talk. So my question was whether this gap between the valid inequality and the SCG cut, you said that it can be arbitrarily large. Does this already hold if S is the set of 0, 1 points?
Yeah, we didn't compute how large can that be, but that can be true. You can actually kind of look at geometrical way. basically you kind of start from a inequality, and then by tilting a little bit, you can make the coefficient arbitrarily large by tilting a little bit. But then you kind of see that the gap remains the same. And the distance between two hyperplanes remain the same. That would mean that the gap is large.
Thanks.
Okay, thank you. And then we have a question from Manarli Sharma. Please go ahead.
So how to find a good S given a polyhedron?
Okay, that kind of involves, I guess, computational questions. If you have an integer program that has some, bounds on variables, then if you just take integer points satisfying those bound constraints, that will be a good candidate for your set S. But computing the corresponding
But
SCG
do you
cut,
think that a good S?
Okay, go ahead.
No, so I was just thinking, fine, is it a good idea to have S as close as possible to the original polyhedron? Because if we take only variable bound, then it may not be a very good approximation of the feasible region of P.
Right. So there's a trade-off. So if you take S to be just polyhedron P itself, then you are just solving the same, same integer program.
Right.
So you can't expect to kind of, get the strongest possible set S. You have to kind of somehow look at small enough S, but also you want to kind of make it easy or simple enough so that you can generate cuts accordingly.
Okay, thank you.
Okay, I think we have time for one question, and from Akul Bansal. Please go ahead.
So I'm thinking like if the S is a subset of P, so like the set of feasible integer solutions is like usually a subset of its relaxation. Can we say something about that?
So again, so if you take S to be the set of integer points in P, that's the same as your original integer program, right?
Right.
Is that your question?
Yeah, that's right. So in that case, what would SCG closure of P would look like?
That's the same as the original polyhedron, right? Basically.
Oh, okay.
So one round of SCG closure would give you the integer hole.
Oh, yeah. Okay.
Right. Yeah.
Okay, I think that were the questions, and that is perfect on time for the next talk. So let's first thank Dabeen with an applause.